Great. Well, thank you both for being here today. Obviously, I'm going to be talking about how we get from, this is a little unclear, but how we get from space dust to us. And as you can see, it's actually kind of simple. All you have to do is knock off a few letters. Right. I'm going to be getting pretty heavy into the assumption of life coming from not Earth. But before we do that, we have to talk about sort of what makes life tick. And both of you are sort of better at this than me, so I'm going to skim through this a bit. I would be talking about organic chemistry, but I'm not an expert on it. So you all know that organic molecules have historically been defined as, I don't know, things that a magic life force can make. So carbohydrates, lipids, proteins, these are really complicated molecules that probably had a hard time just being smashed together randomly. And all the ones that we find here on Earth are really just synthesized by living things. So you can be forgiven for thinking that historically. But then some idiot decided to make them in the lab and completely ruin our definition. So it turns out they do follow the laws of physics. That's all well and good. And if we bring in the idea that maybe there were organic molecules on comets before life evolved, well then it turns out life didn't even start making organic molecules. So that's kind of a linguistic disaster. But the interesting thing is, yeah, space rocks do have organic molecules. Some of them have been found, some of them are constantly theorized and demonstrated that they can form in the conditions of space with stars exploding and all that. But there is one key difference about what we find from meteorites and what we find on Earth. And both of you know that. My astronomy class probably won't. You know what enantiomers are? L&D isomers, equated to the left and right hands for reasons that I don't really care about, except for the fact that they're mirror images of each other and can't be superimposed. And the illustration I have of this is, you take a tetrahedron, so a triangle with three other triangle faces that come to a point in the back. Let's tilt it so that we're seeing its side edge on, and that one corner has gone back a little and the back corner has come forward. Put a carbon atom in the middle, stick an amino and an acid group on here, and at this point, any two corners that you choose, you're free to do whatever. You can still turn it around so that it looks like this. But once we start adding a hydrogen atom to one corner, this is where we come in. Because how are we going to get the thing on the right to look like the thing on the left? We can flip it this way, but then the pink and the blue get messed up. Okay, so we can flip it this way, but congratulations, the hydrogen atom is facing you instead of away from you. So that's not going to work either. And the short answer is it just doesn't. So if we complete the other corner with a CH3 group, we wind up with L&D alanine. And on Earth, all of our alanine is D-alanine. All of our organic molecules, to a very, very good approximation, are all D isomer organic molecules. In space, it's 50-50, a racemic mixture. And that makes sense, because if you're just randomly smashing things together into a carbon atom, then half the time you're getting something pointing left and the other half something pointing right. And this is what we actually find when we synthesize organic molecules ourselves, and how we know that meteorites, the ones on there, actually came from space and weren't contaminated by earthly junk. So now something you might be thinking in your head is, how do we get from the L&D isomer equal mixture, racemic mixtures of space, to the ones on Earth, which are definitely not 50-50. I feel compelled to tell you that the paper I was looking at is like 99% speculation, but that is also very common in the field of astronomy, so let's move on. The first theory that we'll look at, the only theory, because you can only go down one rabbit hole at a time, for reasons that we'll see, pulsars. This is actually the perfect answer, because what better way to address something that you know almost nothing about by bringing in something else that you know almost nothing about? the polarized light is thought to be the key here. The idea being that it might be able to selectively eliminate one of the enantiomers while leaving the other intact. And how that sort of works is, imagine a neutron star, so that would be a remnant of a really big star that ran out of hydrogen, collapsed, and it starts spinning really quickly, and it's expelling beams of X-ray, ultraviolet light at its poles, but that pole might not be, the thing the axis that it spins around. So it winds up just being a spiraling beam that shoots off into space, and it's sort of weird, but space is weird. So if we have a cloud of organic dust that's just sort of passing by, getting relatively close, and getting irradiated, zapped by this beam here, and as long as it spends more time in one hemisphere over the other, then it's plausible to think that maybe some of the enantiomers will get destroyed and shift the balance from left to right. So how we see if light can actually do that, what we do is take a bunch of racemic tryptophan, so 50% L, 50% D. You may or may not have heard that turkey is a high source of tryptophan. I don't know if that's true or not, but we stick it in a cooler that's about 10 kelvins to mimic the conditions of space, blast it with a laser for 100 hours. Here are the technical specifications. It's ultraviolet light with a mercury lamp, circularly polarized light, but I imagine that's what the experimental setup looked like. What do we get? So again, we started with a 1-to-1 ratio of D to L isomers, and after 2 trials, I wound up with a 1.02 to 1 and a 1.033 to 1 ratio. So about a 2 or 3.3% enantiomeric excess. So that's a kind of small number, but it's consistent and it registers. So I guess that means we're good. Again, astronomy, fast and loose with numbers. But the authors do point out that, well, maybe it was even more effective than we thought, because the sample that they used was 20 times thicker than what UV light could go through. So if we take into account only the amount of material that was interacting with the light, we might wind up with an enantiomeric excess of even 50%, so a 1.5 to 1 ratio, which is actually pretty huge, especially if you're thinking about the amount of time that it's been there. Just 100 hours is not long at all in space terms. All right, so once we get a general feel for how many neutron stars there are in a galaxy and how long a cloud of organic dust might just sort of surround or interact with one of these neutron stars to get the conditions that we had in the lab, we throw it all together and get a ballpark figure of about. I'm going to explain what I mean by these letters and ignore anything else that you might see here. The probability of having an enantiomeric excess of 50% is about 1 in 100%. So that's not too bad. It registers, which is a lot more than you can say for a lot of physics. And if we relax that condition, the probability of having an excess of 10%, 1.1 to 1 ratio, is 1 in 10. That is a number that is almost unheard of in the field of astronomy. And it's, forget about significances in statistics for a moment, although that is pretty close. 1 in 10 is a very decent chance of something happening. It is not too far-fetched to think with these results that a lot of pre-solar dust clouds that form solar systems like ours might have started out with an enantiomeric excess in one direction or another of about 10%. So, we figured out something good today. The final thing that we have to take into account is we get from up there to down here without parachutes or rockets. So it turns out organic molecules stay in comets for very long periods of time, and it's totally good. It's cold out there, there's nothing really there to bother them until you douse in the sea of flames. Then things aren't so pretty. But luckily we have a few things working on our side. The first is atmospheric cushioning, where the comet, as it comes in, will be slowed down by an atmosphere probably 20 times thicker than the one that we have today, but regardless. So it's not going to explode into a big fiery mess as soon as it hits the Earth, so that's good. There's also the idea of fragmentation from expansion shocks, and as things vaporize from the heat of friction, namely ice to water, it'll destabilize the comet and break it apart while it's still in midair. And smaller things have smaller terminal velocities, greater surface area to mass ratio. So then what happens is these particles just sort of float gently down to the surface of the Earth. We hope they do. And the last thing is ice. A lot of these organic molecule particles are grains of dust, so a few micrometers in diameter in size. And they are generally surrounded by a layer of ice. And what happens is that this ice takes the brunt of the heat, and it protects the organic molecules from being pyrolyzed or destroyed by heat, essentially. So we did it. All is right with the world. Literally. Right is... You know what I mean by that. Oh wait, we still have to get to humans, don't we? Okay. So the idea after impact is that we get a crater, the ice melts, there's a high concentration of, this is one idea by the way, there are many others, high concentration of organic molecules in there, just sort of crashing into each other at a much higher temperature than they were in space, to make, possibly, a lot of molecules, organic and otherwise. And we'll get some monomers out of this maybe, and those monomers, given enough time, might link into each other and make polymers. We get some protoenzymes, where there's some natural catalytic activity going on, and if it gets surrounded by a shell of amino acids, it can be protected and just keep driving those reactions for a long time. If we develop lipid bilayers, then we suddenly are able to have compartmentalized reactions, and with the advent of metabolism, the ability to control the rate of these reactions, we get life. And then we have to get multicellular life. Sponges are the simplest animals. I don't think they're the first multicellular life, though. I think they're very far from that. And then we gotta develop all these other characteristics, including intelligence, and we finally get us. Hello. So, do we know if this story is even remotely true? No. We probably won't be able to for a very long time, or forever, because we just don't have the data. But I think there is something inherently attractive about speculating about all this. I think it comes back to a satisfaction that we crave in being the masters of ourselves, our environment, and our own natural history. And some people find that process entertaining, and I hope it's been entertaining to you. So thank you for putting up with me.